That airplane wing outside the window is bending. Not a little, not almost imperceptibly. It is bending by meters. And if that wing were perfectly rigid, the plane you're sitting in would be far more dangerous than you realize. In the next minutes, you're going to understand why airplane wings are designed to flex, why engineers deliberately allow them to bend under extreme loads, and why making them stronger and stiffer would actually bring them closer to failure. If you enjoy understanding how invisible engineering decisions keep extreme machines alive, subscribe to the channel. This is Critical Limits. Most people imagine airplane wings as solid, rigid structures. From the ground, they look stiff. From pictures, they look unmoving. From diagrams, they look like solid beams attached to the fuselage. But in reality, an airplane wing is one of the most flexible major structures humans have ever put into the sky. During normal flight, wings bend upward. During turbulence, they bend more. During extreme maneuvers, they can bend dramatically. In some certified tests, wings bend so far upward that the tips rise higher than the top of the fuselage, and they do not break. That bending is not a flaw. It is the entire point. To understand why, you need to forget how you think about strength. Most people believe strength means resisting movement. The stiffer something is, the stronger it must be. That intuition works for small, simple objects. It completely fails for large, dynamic systems. An airplane wing is not just carrying weight. It is fighting air. At cruise altitude, air might feel thin, but at hundreds of kilometers per hour, it behaves like a solid mass pushing back against the wing. Lift is not gentle. Lift is force, and that force is not constant. Every gust, every thermal, every pocket of turbulence, every maneuver, all of them apply changing loads to the wing. Not once, not twice, but millions of times over the life of an aircraft. This is where the real danger appears. A wing does not fail because of one large force. It fails because of many smaller forces applied repeatedly. This is called fatigue. If you apply a single heavy load to steel and remove it, the steel can survive enormous stress. But if you apply smaller loads over and over again, microscopic damage begins to form. Tiny cracks, invisible flaws, changes in the internal structure of the material. At first they don't matter. The wing still works. The plane still flies. Everything looks fine. But each cycle adds damage. And eventually, something reaches a critical limit. Now imagine a perfectly rigid wing. A wing that refuses to bend. Every gust would be absorbed internally. Every force would be trapped inside the structure. Energy would have nowhere to go. Instead of moving, the wing would store stress. Stress concentrates. Stress accumulates. Stress searches for the weakest point. And when it finds it, failure is sudden. This is why rigidity is dangerous. Flexibility is not weakness. Flexibility is controlled survival. When a wing bends, it does something crucial. It dissipates energy. Instead of storing all the force internally, the structure moves slightly, spreading stress across a larger area and over a longer time. That movement reduces peak stress. Lower peak stress means slower fatigue. Slower fatigue means longer life. Engineers are not trying to stop wings from bending. They are trying to control how they bend. This control begins deep inside the wing. An airplane wing is not a hollow shell. It is a complex internal structure made of spars, ribs, stringers, and skin. The spars carry the main bending loads. The ribs maintain shape. The skin distributes stress. Together, they create a structure that is stiff in some directions and flexible in others. This is not accidental. The wing must be stiff enough to hold its aerodynamic shape, but flexible enough to absorb loads without breaking. Finding that balance is one of the hardest problems in aerospace engineering. too flexible, and the wing deforms excessively. Lift changes. Control surfaces lose effectiveness. The aircraft becomes unstable, too stiff, and the wing becomes a stress trap. Fatigue accelerates. Failure becomes more likely. So engineers aim for a very narrow window. Strong, but not too strong. This balance becomes even more critical during turbulence. Turbulence is not just uncomfortable air. It is rapidly changing airflow that applies alternating loads to the wing. Up, down, up, down. Each oscillation is a fatigue cycle. If the wing were rigid, each cycle would hit the structure like a hammer. But because the wing flexes, part of that energy is absorbed by motion. The wing moves with the air instead of fighting it. This is why, counterintuitively, a flexible wing often experiences less structural stress than a rigid one. The wing yields slightly, so it doesn't have to resist fully. This idea extends to extreme cases. During certification tests, manufacturers push wings far beyond normal flight loads. They attach hydraulic actuators. They bend the wings upward. They keep pushing. The wing bends, and bends, and bends. The test does not stop when the wing looks scary. It stops when it reaches a specific multiple of the maximum expected load. Only then is the wing allowed to fail. And when it fails, engineers learn exactly how and where. Those tests reveal something important. Wings don't suddenly snap under normal conditions. They fail only when pushed far beyond anything they will see in service. Because the bending is planned, expected, engineered. This also explains something passengers often notice. During turbulence, you may feel the plane shaking, but the wings appear calm. Or you may see the wings moving while the cabin feels stable. That movement is protecting you. The wing is acting like a suspension system. Just like a car suspension absorbs bumps so the cabin doesn't experience every vibration. The wing absorbs aerodynamic loads so the fuselage and passengers don't experience the full force. Now consider the alternative. A rigid wing would transfer loads directly into the fuselage. Every gust would be felt more sharply. Every maneuver would stress the entire aircraft more severely. Comfort would decrease. Structural fatigue would increase. Maintenance costs would skyrocket, and the margin between safe operation and failure would shrink. This is why older aircraft designs, which tended to be stiffer, required heavier structures and more frequent inspections. Modern aircraft use advanced materials and design techniques to tailor flexibility precisely where it is needed. Composite materials allow engineers to orient fibers in specific directions. That means stiffness can be increased in one direction and reduced in another. The wing becomes anisotropic, strong where it must be, flexible where it should be. This is not about making wings weak. It is about making them intelligent. Another misconception is that bending means damage. Passengers see the wing flex and assume something is wrong. In reality, damage is usually associated with cracks, permanent deformation, or loss of shape. Elastic bending is none of those. As long as the wing returns to its original shape after the load is removed, it is operating exactly as designed. That return is critical. The wing is not meant to stay bent. It is meant to flex and recover. If it did not recover, that would indicate plastic deformation. That would be a problem. But elastic bending is safe, expected, necessary. This brings us to an uncomfortable truth. If you never saw the wings bend, that would be more worrying. It would suggest the wing is absorbing energy internally without releasing it through motion. That is how structures age faster. That is how fatigue accelerates silently. This principle applies far beyond aviation. Bridges flex under traffic. Skyscrapers sway in the wind. Ships bend with waves. Every large structure that survives dynamic environments does so by yielding in controlled ways. Absolute rigidity is a fantasy, and a dangerous one. In aviation, engineers are painfully aware of this. That's why they design wings to bend long before they allow them to break. They choose materials that can endure millions of cycles. They test for fatigue relentlessly. They monitor structures throughout the aircraft's life. And even then, margins exist, large ones. Because aviation does not tolerate sudden failure, the wing is not just holding the plane up. It is negotiating with physics. Every second, every gust, every mile, it absorbs, it releases, it balances. That balance is invisible from the ground. Passengers see a smooth flight. Pilots see stable controls. The structure quietly does its job. This is the hidden genius of airplane wings. They look solid. They feel strong. But their real strength lies in knowing when to yield. Not too much, not too little. Just enough to survive forces that would tear a rigid structure apart. So the next time you look out the window and see the wing bending upward, remember this. That movement is not a warning sign. It is proof that the wing is alive. Responding, adapting, protecting the aircraft. In engineering, the most dangerous structures are not the ones that move. They are the ones that refuse to. And that is why airplane wings are never rigid. Not because engineers couldn't make them that way, but because they know exactly what would happen if they did. That bending you see is not weakness. It is the aircraft staying safely below its critical limit.